Hi everyone, this is Xuejing from the University of Hong Kong. My supervisor is Bruno Oliveira. Today, I'll present our paper about a type-directed operational semantics for a calculus with a merge operator. Let's have a look of our lambda I calculus first. It supports intersection types like int and bool, as well as the merge operator for terms. These two constructors are similar to product types and pairs, which are often associated with logic conjunction. However, to eliminate a term of a product type, we need two eliminators, while merges are eliminated in an implicit way. The implicit elimination of merges make it hard to design the evaluation relation, and many previous works give the semantics by elaborating to a target language. By contrast, our calculus has a direct operational semantics that enjoys both determinism and subject reduction. As a consequence, we have a simpler proof of unambiguity and deal with recursion in a straightforward way when reasoning becomes more direct. Much work on intersection types has focused on refinement intersections, which only increases the expressive power of types. In those systems, the disjointed type, the intersection type int and bool is invalid since they are not a refinement of each other. With the merge operator, we can construct values that inhabit int and bool and therefore gain more expressiveness in term level. As Dunfeld argues, intersection types with a merge operator provide general mechanisms that subsume many different features. One existing application is typed first-class traits. Traits in OOP offer a model of multiple inheritance. A trait, like a missing, contains some methods. In the right program, inheritance is encoded as a merge, and the traits can be dynamically constructed in a type-safe way. Other object-oriented features that can be encoded via the merge operator include dynamic missings and forms of family polymorphism. These highly dynamic forms of object composition are not available in current mainstream languages, such as Scala or Java. If you have attended the talk just before the last Meet the Speaker session, you may have noted it benefits from the merge operator as well. With merges, disjoint polymorphism can encode essential aspects of row polymorphism and bounded quantifications. Despite over 30 years of research, the semantics of the merge operator has proved to be quite elusive. In Rena's fourth language, a merge is permitted only when the second term is a lambda abstraction or a record, which makes it impossible to merge functions. What's more, its approach is unable to reduce merges when multiple primitive types are required. The calculus lambda end proposed by Castegan and others has a restricted version of the merge operator for functions only. This merge operator is indexed by a list of types of its components, and its reduction requires runtime type checking. Peirce was the first to briefly consider a calculus with an unrestricted merge operator, but he did not study the dynamic semantics. Finally, Dunfeld goes further and presents a direct operational semantics for a calculus with an unrestricted merge operator. However, the problem is that subject reduction and determinism are lost. Let's have a closer look of Dunfeld's semantics. The two parts of the merge are treated so equivalently that even the two rules on the top are overlapped. But that source of non-determinism can be easily fixed by forcing an evaluation order. The next two rules reveal the key of the peculiar behavior of merges: implicit elimination, which leads to non-deterministic results, and ER-typed programs, as the left examples show. Additionally, by the last rule, any expression can split into a merge of two copies of it anytime. So, how are we going to control the merges? In our system, firstly, we address the type preservation issue with the help of type annotations. With proper type annotation, a merge can drop any of its components and even rearrange them, achieving similar effect of Dunfeld's rules. While a merge of two values does not stop when it stands alone. And lambdas are fully annotated, therefore no runtime type checking is required when dealing with functions of merges. As the right example shows, the right part of merge is used in the application, and the previous ER-typed program is avoided now. To reduce such annotated value, our reduction rule triggers a typed reduction relation, which reduces a value against a type, and produce a value of that type, working like a coercion with owning the target type. For example, on the type int, 1 merged with true is reduced to 1. On the type bool, the same term is reduced to true. Besides the annotation rule, our beta reduction rule also triggers type reduction, which filters the input value by the lambda's input type. So given a merge of 1 and true as the input, the identity function, when annotated with int to int, only takes the int part. However, with type preservation, the non-determinism problem remains. Although 1 or true can be selected by int or bool, sometimes we cannot distinguish parts of merges from their types. For example, what should the type reduction produce when reducing 1 merged with 2 against the int? 1 or 2? So we choose to reject such ambiguous merges in the typing rule of merge by examining their types. Merging two integers are forbidden. This restriction we posed on merges is called disjointness. It comes from the lambda I calculus by Oliveira and others. Two types are disjoint only when they are not overlapped, like int and bool. Int is not disjoint with int and bool, since they both have type int. Therefore, all well-typed merges in our system cannot lead to non-determinism when reduced under certain types. Although we have obtained determinism, type preservation breaks again. Do you remember the split rule in Dunfeld's semantics? Our typed reduction can copy values as well, and the result obviously violates the typed disjointness constraint. So we generate EL-typed values by ourselves. But such merges are harmless, as no matter which side is chosen later, when reduced against int, the result is the same, 1. Therefore, we add another rule that relaxes the disjointness constraint for merged values owning. This consistency checking ensures that when the two components of a merge coincide on types, the overlap parts are always equal. That is to say, if they can both reduce on the one type, you are free to choose either result without worrying about non-determinism. For instance, 1 is consistent with 1, so 1 merged with 1 can pass the type checker. Similarly, we can merge 1 with 1 and 2. But ambiguous terms like 1 merged with 2 are still rejected, because when reducing against the same type int, they have different results. To be noted, when two values have disjoint types, they must be consistent. Now we have the two wanted properties. Let's relate our system with other calculi by two theorems. Firstly, compare with the semantics of Dunfeld. Our operational semantic is proved to be sound, with some minor extension to Dunfeld's semantics. That is to say, any step in our type-directed operational semantic corresponds to 0, 1, or multiple steps in Dunfeld's semantics. Secondly, our type system is complete to lambda i's type system in the sense that all its programs can be elaborated into our language. Our system is able to type check any well-typed term in lambda I with proper type annotation inserted based on the typing derivation. In summary, our contributions in this work are: first, designing a deterministic and type-sound type-directed operational semantics for lambda I NO, which is a calculus with intersection types and a merge operator. Second, using a new proof method that deals with recursion, while previous calculi with disjoint intersection types cannot, due to the elimination of the current proof approaches for coherence. Third, we propose the novel notations of typed reduction and consistency, which are useful to prove determinism and subject reductions. Fourth, we relate our calculus with the calculi proposed by Dunfeld and Oliveira and others by the soundness and completeness theorem. We also compare our calculus with other calculi with intersection types in the paper. Fifth, we formalize all the results in ECOOP, the theorem prover, and they are available in the supplemental material. You are welcome to investigate. Thanks for your listening. That's all for today.